بسم الله الرحمن الرحيم. السلام عليكم. In this tutorial we'll solve problems dealing with different steady state devices. So we'll start with this one for 37. We have air expand through a turbine operating at steady state. So turbine, we'll use this symbol of the turbine. So this is the inlet and that's the outlet, and this is turbine which will develop power of W. So the inlet number 1 and the outlet is number 2. So the inlet we have P1 equals 1103 kilopascal and T1 equals 867 Kelvin. P2 the outlet, this is 102 kilopascal. Okay, the mass flow rate of air entering the turbine. So this is the mass flow rate equals 4.8 kilogram per second. Of course, since this is steady state, then m.1 equals m.2. Okay, and the power developed equals to, so this W 1900 kilowatt. Neglecting heat transfer and kinetic and potential energy, determine the exit temperature T2. So we need to find what is T2 in Kelvin. So this is straightforward. If you write the energy equation, so Q dot minus W dot plus M dot H1 minus H2, and we are using this form because here we have only one inlet and one outlet, so we can combine the inlet and outlet in one bracket. Since there is no potential or kinetic energy change, then this will be the only thing inside the bracket, and this will equal to 0 because it is steady state. Now the heat transfer is 0, so we have this relation. Now we can do this two ways. Okay, we can either use tables, so variable specific heat, okay, and that's, by that we mean that we'll use the tables, air tables, and by that we'll say, okay, now if we use tables, then we can get H1 from T1, so H2 from this equation, okay, will be H2 will equal H1 minus W dot over M dot. Okay, and we have the temperature of 867, so we go to table A22 for ideal gas air, and 867 is somewhere between these two values, and so we can do interpolation and find what is T2. Okay, so this is T1 here, and this is T1. T1 equal 867, right? Yes, Kelvin. So we can find H1 through the interpolation, and then we just substitute for W dot and M dot, and by that we'll get H2. Now, knowing H2, we can go back to the table A22 and do the reverse thing. So we know H, and from H we know what is the temperature. Okay, so from table A22 using H2 we find what is T2. So this is one way. The other method is to assume constant specific heat Cp, and by that what we'll have here is that minus W dot plus M dot Cp T1 minus T2. Okay, this will equal to 0. Now we need to find Cp, and we have the temperature of T1 equal 867. So we go to table A20 and use the part of air. We have 867, so we are between these two, and we need to find what is Cp. So again, we can interpolate. Here we have 867. We can get what is Cp between 1099 and 1.121. So we can do that and find Cp, and by that we can find what is T2 equals Cp, no, T2 equals T1 minus W dot over M dot Cp. Yeah. And that's how to find the temperature. In the question, if nothing is said here, like what you have here in this question, then you are free to use either this method or that method. But most likely there will be statement that, for example, assume constant specific heat. Then you will need to use this one. Or if it's if it says assume or use variable specific heat, then you will need to use the tables. Okay. The second question here is 448. Here we have refrigerant 134A enters air conditioner compressor. So compressor, we use this symbol of compressor. This is the inlet 1, and here the outlet 2, and again this is W dot, and this will be N. We need power to operate the compressor. Okay, so here we have enters the air, and we shouldn't. So this is R134A. This is the substance that we deal. So we have P1 equal 3.2 bar. We have T1 equals 10 degrees centigrade. Then P2 equals 10 bar, and T2 equals 70 degrees centigrade. We have the volumetric, so V dot equals 3.0 cubic meter per minute. And here we should really read question carefully. Here it says the volumetric flow rate of the refrigerant entering. So this is V dot 1. Okay, and the reason is that V dot 1, okay, V dot 1 will not equal V dot 2 because this is compressor, so it will compress. Therefore, the density will change. Therefore, the volumetric flow rate will be different. Of course, the mass flow rate m dot 1 will equal m dot 2. Okay, because it has only one inlet and one outlet, so the mass flow rate should be the same for the conservation of mass. Okay, now the power input to the compressor, so this is power input to the compressor, is 55.2 kilojoule per kilogram of the refrigerant flowing. Neglecting the kinetic and the potential energy effects determine the heat transfer. So here we have compressor, but we still have heat transfer, and we need to find it in kilowatts. So the heat transfer is not always zero with the compressors or the turbine. Okay, so what we have here, we need to use the energy equation. So Q dot equal Q dot minus W dot plus M dot, and again all what we have is H1 minus H2. The kinetic and the potential energy effect is to be negligible, so this will equal to 0 because it is steady state. Now Q is not 0, so and we need to find it. So we have Q dot equals W dot plus M dot H1 minus H2. Sorry, okay, since this will go to the other side, then this is H2 minus H1, okay, because this will be negative when it goes to the right hand side. Okay, now we already have W dot, but this is in kilojoule per kilogram, so this is actually the specific work or specific power, okay, per kilogram. So what we have here is that this will equal m dot times omega, which is this one, okay, plus m dot H2 minus H1. Okay, so this is m dot omega plus H2 minus H1. This is Q dot. Now we need to find m dot. All what we have is the volumetric efficiency, but we can find this because here at the inlet we have two independent and intensive properties, and also at the outlet. But we need to know what is the region of this, okay, what phase is this one. So we go to the table. So the pressure is 3.2 bar and temperature is 10. So if we go to the saturated liquid vapor mixture table for refrigerant 134A, you need to be careful to use the right table. So we have pressure is the pressure is 3.2 bar, so it's this one, okay. Here we have the temperature is 2.48. this is the saturation temperature, and our temperature is actually 10 degrees centigrade. So our temperature is larger than the saturation temperature, therefore this is superheated vapor. So we go to the superheated vapor table for 3.2 bar for the refrigerant 134 and temperature of 10. So this is the temperature of 10, okay, and this is H, and and this is V. So this is V1 and this is H1. Okay, so from V1 we can get m dot equals V dot 1 over V1. We have both, then we can get m dot. So m dot is found. H1 also we found it from the table, and for H2 we have also pressure and temperature. So we need pressure 10 bar. We have the pressure is 10 bar and the temperature is 70. So pressure of 10 bar is this. Okay, and here again the saturation temperature is 39.39, but our temperature is 70. So again the temperature is greater than the saturation temperature, therefore it is in the same thing, superheated region. So we go to the superheated region table of 10 bar and temperature of 70, and this will be our H. So this is H2. Okay. Now there is something here important that you need to notice. Okay, so let me write it. So here Q dot equal m dot times W. What is W? W is 55.2, but this is input, and input work is negative. So this is minus 55.2 plus H2, which is 302.34, 302.34, minus H1, which is 255.67, 255.67. So this is what we have, and you notice here that the result will be negative. Okay, and so this will be in kilowatt. So the heat transfer, negative heat transfer, means that the heat transfer is lost to surrounding. Okay, thank you.